Okay, everybody, welcome back. Welcome to the least pre-planned session of PKC, in which we discuss some very new work that has recently been posted to the ISDR ePrint archive about quantum algorithms for lattice problems. I'd like to thank very much our four panelists for agreeing to lead the discussion at such short notice. Daniele Micciancio, Nadia Heninger, Gabrielle De Michelli, and Long Chen have all volunteered to lead the discussion, but of course it's going to be much more of an open discussion rather than a talk. So before we begin, I have to rectify something I forgot to do during Nadia's talk, which is this very high quality certificate of appreciation for coming and invited speaker. And I'm trying to see myself. I will look at a very giving present. Now, with just a short opinion from each panel member, then we're going to have a couple of questions from us, and then we're going to open the floor to anybody who would like to ask a question, either about the paper or about its implications more generally. So while you're sitting there eating your lunch, start thinking of questions to ask. That's very much.
First, I guess most of you have already noticed the big new breakthrough of the algorithm, which is the gradient works done by e-learning. I'm trying to read the paper the submission. Yeah, the peer review. So I guess it's too early whether the algorithm in English is really correct. And we're still waiting for the peer review results. But in this time, I just something about my opinion, my personal opinion. I guess although I spent many years of studying problems, but I'm not an expert on program theory. There are only a few very talented experts are had by some confidence to and secret. But just from my personal opinion, I guess the paper is very breakthrough results. And if it's correct, this might be especially the standardization of the protocol. And we found that these have already submitted higher with some of the national standard. But I think when this algorithm is published or you finally publish grading review, it will give a great output to boost higher or standardization. People will be very curious or very doubting about the online security. Already, many of us already noticed that the paper now claim is totally correct, however, all the spec parameters for the language problem like the level of services you use it. But already, I guess it can indeed compress many of the parameters of what HLP is. So it's a totally new algorithm, but if they have some follow-up work, whether it will be one day where it can totally break all parameters. I don't know. I don't think about it. But personal opinion, I'm more realized I'm more I really not be totally break like component. Why? Because if I looked in the paper, it was said for the certain parameters, for example, the modular, the type algorithm closely related to the especially the modular we choose the modular of WQ to the approximately to the square of n dimension of the lattice can apply, but when we the one modulus is gets smaller than the bound, then this concept cannot apply right now. So people might be curious, but if whether we can find a smaller can optimize the attacking algorithm. I don't know. But this is because when we choose a small enough cube, the algorithm even can be statistical different with the uniform distribution. That means the north area is very large comparing to the oil modulus. So if we go into the line that we might think that for certain parameter Q, it is statistical hard, but if Q some larger, and if even it is a result is right, when Q goes to the square of n, and it can be polynomially solved by quantum algorithm, and I guess in the middle, we can find some point that the Q, for some parameters Q, that for some parameters Q, that the algorithm problem can be computational hard. But currently we do not know. Yeah, so, we do not, but currently we do not know that point. Actually, we need to the world, all the genesis in the world of talented cryptography and in the world, we keep efforts to this world and find the region that where where to which point that the algorithm can be can be dimensional hard and to which point it can be solved in polynomial. That's a different point.
So my opinion on this paper is it doesn't have and I think that it's not paper. Kind of very complicated paper that not well your understanding, which makes it very important to verify the correctness, which is where we could get small errors in these formulas. The one thing that I think I would be interested in understanding is to see if there is an error in this paper, whether it is a fundamental error in the reasoning in the structure of the attack, or whether it is most likely small errors and that can be easily corrected. And going in the direction of the parameters as I was saying before, so also understanding whether what are the limits of the attack, how do we push the attacks in if the attack is correct, or if it is not completely correct, can be corrected. It's the fundamental way that can the attack correct, can be improved, and to what point can be pushed. So that would be understand doing that for us. I think the thing that is most interesting about this paper is both online and nobody understands it. About 5 people who were like qualified to actually understand and read this paper, And I have talked to a couple of them and, you know, sort of gossiped about who is reading it and what their opinions are with some other people. Nobody understands. Like it is very complicated. Even the people who have co-authored papers with authors don't understand. There's a bunch of new ideas, but it's obviously sort of, as Bob mentioned, very closely connected to the exact parameters. And it's 50 pages of just all the formulas. The probability that there is a mistake somewhere in there, as I said, is totally one. And so, yes, the interesting question is it a minor mistake that doesn't change the character of the results? Is it a major mistake, but there's still some kind of fundamental interesting underlying idea that gives us a non-trivial foothold into quantum algorithms for lattices, or is it totally bad? I have no idea which, and I don't even know, you know, if it's under submission, are the three so anyway, if you look at the acknowledgements, you can see there's history to this idea. So even though you like look at the paper and it's a wall of text, you can look at the acknowledgements and see that he has done this before. He's had these ideas before and are good bugs. And so there is like a history of going back and forth. So it is hard to say one way or another, but I would be willing to say that there's a probability one there is some error in it. Need more than 5 people to do this kind of thing. I think that's the main thing that is highlighting, but she's not best to be 5 people in the world that are entire opinion of the lattice-based crypto systems that we are about to tell everybody to deploy.
First of all, I will point out that these 5 people in the world that can read the paper, they also have other things to do. And so this is not a simple process. But so there is also something about the post-quantum cryptanalysis that we should consider. Now, differently from the standard type of cryptanalysis, where you have a classic algorithm, and whether or not the proof is correct, you can think of implementing it, running it, see if it works at all in smaller distances. In the case of quantum, we cannot do anything like that, which is something that could give some confidence about the validity of the attack without understanding and verifying all the details of the mathematical proof. Now, I don't know if from a quantum computing standpoint, is it feasible to do anything that could help validate to some extent experimentally what's behind not just this, but also behind other type of similar post-quantum attacks that could come up in the future. Now, so besides this, I also wanted to present you with 2 possible scenarios. Now, of course, the question that is in everybody's mind right now is this result correct or not? We don't know. It will take a little bit of time to find out. But let's assume that it's correct. I think there are 2 possibilities here, and I cannot really tell which of the 2 is the most likely one. Now, one is that, okay, so we have this attack. The attack shows how to use quantum computers to approximate lattice problems within a certain polynomial factor. The factor is n to the 4.5 currently. Now, we know that the lattice problems, they can change quite a bit depending on the approximation factor. For example, n approximating within a factor n is a factor that seems connected to the problem being in certain complexity classes or square root of n. We know that the problem may go from NP hard to NP easy in the sense of being also in co-NP, so unlikely to be NP hard when the approximation factor crosses square root of n. So it is also possible that perhaps the problem is hard for approximation factors that are linear or quadratic in the dimension, and then it becomes easy after that. So the fact that we have this result is not something that necessarily tell us a lot about the possibility of basing the public key cryptography or even certain types of FAQ schemes on lattice problems. So that's one possibility. So the problem is secure. It's just that we thought that the lattice problems were much harder than what they are now, but what we can do with them didn't really change. It's substantially the same. So this is one possibility. This is the optimistic thing that could be the conclusion if the result is correct. Now there is also one possibility, which is sort of a nightmare scenario, which is what I felt like, okay, so if this result is true, we may be in a world where, in a post-quantum world, where public cryptography just does not exist. So it's not a matter of changing the problem. We know that public key encryption requires structured problems which are hard, not just one we find, but structural hardness. And there could be something fundamental that says that this type of structural hardness, which is required for public key encryption, is something that in a post-quantum world cannot possibly exist. And it's not about lattices, there is something more fundamental there. Now, which of the two, in which of the two worlds we live in? Well, I can tell you which one I would rather be in. I don't really know which one is the more likely. It could be way worse than what everybody was worried about when we first saw the paper. So I guess we can move to the questions.
And we're already expanding leading the discussion to a more broader sense. So can you describe a potential very optimistic world, very pessimistic world? Even though we don't know where we are, then what do you think, like as a community, what should we, how should we respond? What should we do?
And is a very big it is. So if these results turns out to be correct, I think we should seriously consider what to do if public key encryption does not exist. So this is something that requires not just, okay, let's invest a lot in research, in math to try to find a better problem. It's something that would drastically change we can use the internet. And it's something that will require some time to think about, get used to the idea, and even as a possibility, is something that we don't want to be completely prepared for.
And I feel obligated to bring up some ideas for the existing possibilities for a world where public. Two historical examples are key distribution centers, and both of these, I mean, they would work in a sense to connect to the internet. And then you have like the government service provider, who you go and sign up and you get your key with the government distribution center, and you connect to them and they give you your session key. Which enables a world of surveillance, right? The other option is quantum key distribution, which the physicists would love. And this also sort of enables a world of surveillance because it's point-to-point protocol. And so, you know, your data is encrypted point-to-point, but then you like decrypted and re-encrypted periodically, which also is wonderful for people who would like to surveil. So just putting out there that the solutions that we have enable surveillance futures. Have-based signature was probably okay with though, right?
Signature, so.
So like authentication.
no matter if this result is correct or not, definitely it creates a lot of new thoughts about that. Also, like as pointed by Nadia in my talk, we at least need to make sure like that the world has more than 5 people to validate such a and do you have any thoughts like how should we and Nadia actually Nadia also mentioned how do we actually make the validation of such kind of attacks in the future potentially easier? And how do we encourage such type of crypto analysis works?
Giant piles of money.
I would be mind. These are hard to read papers that require a lot of expertise and training. This is a quantum algorithm. Okay.
That's a really big pile. If somebody gave you $10 million, would you drop everything?
Yeah, no. Few people, but the people that can do that, they're not that many. So what should we do? Start teaching some quantum in elementary school, and then bigger, population of experts. It's a technical area. So it's, yeah, I don't think it's something that can be addressed just. It would be good if the people that read the paper could put everything else aside of the things that they have to do, and they could just focus on that when needed. Sure, that would be useful, but it's yeah. If you want more people in the area, yeah, it's something that requires some other mechanism. Yeah, I'm not entirely sure how that could be done.
So you can formally decide.
Oh, yeah. When we should be. He submitted some. It's already has to read it, but if the author would volunteer to present his paper in seminars in front of experts, go through the details of this. This could be a way to verify it collectively. And of course, it would be, the author presented his own work, so he would be able to present it assuming it is correct, but then it would be some sort of verification,
Asking if you would like to participate in this or not.
Oh, okay.
Yeah, actually.
And you might participate in the papers in general.
Students who will be for nowadays, we can get more job opportunities. Yeah. But if we cannot, one we cannot proceed as outcome in 1 or 2 years, making the result in people. This is very challenging. We cannot use it for results to apply companies, and we call on we make livings to. This is a global problem, I guess. And this is a good lesson. We do a lot story to the government.
Well, it's been a little bit on the giant pile. Because I mean, money enables a lot of things. It enables you to buy time. You can buy faculty away from it. Pay for students to spend literally years to become world experts. Schools where. And I think there is a gap because so there's people who are doing quantum algorithms. We have Lattice stuff, but the overlap between them is actually quite small. Things like you said, papers. And I think I don't know if there's a kind of like a dedicated push of like we absolutely need to have like big confidence, which means we need like I don't know. Few hundred people who spend all of their time thinking about quantum algorithms for lattice things. This would cost money, but you could do it in 10 years or something if you wanted to. So maybe, I don't know, we could write like requires a more organized investment than we actually have.
Of this type of results and claims. But in other areas of computer science, there is increasing interest in the formal verification of the proofs. So this is something that in mathematics is also receiving more and more attention. And personally, I think that our current standards of checking the validity of results, exemplified by the peer reviewing process, which is good. I'm not saying that it's not good as it is. I think there's not quite ideal, meaning that the chances of a paper containing a bug, even after having been reviewed by 3 people, 3 experts, is not something that you can really bet much on. So typically the situation is that if the result is very important to get the attention of many other people, then a lot of people will look at it and then will have more confidence in the correctness of the result. But it's not something that is addressed in a satisfactory way just by the standard peer reviewing approach. So the way we write the papers, including myself, I'm putting everybody in this category, I'm not singling out the paper mistake. So that paper is hard to read. So there are many cryptography papers that are hard to read. And we just don't put enough importance on making our papers easier to read. So there's a lot of focus in explaining why the result is important, why the problem is important, and all these other good things about it, the storytelling part of the paper. And the proof often, the proof of security is left as some kind of technical detail that perhaps, I mean, what is the incentive? Most authors think that nobody is going to read the proofs anyway. I think that's how many people feel, because if they felt that it is important to have proofs that can be read and understood by people, perhaps things would be better. Now, getting to the point where proofs can be mechanically checked, that's a big change. We are not going to get there from one day to the next, especially when it comes to quantum algorithms. But perhaps it may be useful to try to move things a little bit in that direction. Putting more emphasis on making proofs to some extent verifiable with less phosphor.
When I looks like not only really give us more verification for those small jobs. And I think we should open to the audience if you have any questions.
Get out of worlds, one where the result is true and possibly extends to a certain parameter set, and the second way is that okay, it might just completely quantum, might just completely destroy complicated. And now quantum computer has come a long way. It's been here and there almost as long as normal computers, and there has been a lot of work in the past 50 years. But it's just a little bit more mature than, let's say, Tuesday or something, right? It's always this 10-year concept where people say in 10 years we have universal quantum computing, but we still have not had a single large scale or somewhat universal quantum computing. So even if the result is true, it might be that there's a third world, which basically is okay, if there was a quantum algorithm, if there was a quantum computer, we could describe having cryptography, but it might just be that dimension will not be added to the quantum computer in the next 100 years or something. So then you would have to move from assumption that is okay, nobody can build an algorithm that can break out one fast enough to something nobody can build a quantum. What do you think?
So I mean, if the situation is that you can break lattice cryptography in polynomial time using quantum computers, but we cannot build those quantum computers, I don't see that much different from using factoring. So when we'll be at a point where we can build a quantum computer capable of factoring numbers. So yeah, we don't think this is going to happen from one day to the next. But at the same time, it wouldn't be clear if the transition between factoring to a different problem is really different from that point of view. Anything else? Yeah.
I would like to propose another sort of intermediate state where perhaps the current algorithm is not fully correct, but there is something to it. So it gives, say, the sub-exponential time quantum. Very large polynomial, I don't know, slightly larger than polynomial approximation factor, which would put us all in limbo for a long time, because the reason that people are so excited about lattices for post-quantum cryptography is that we seem to have approaches they can seem to be sort of vulnerable. We know everything, but then everybody's kind of not sure where we stand. That would be, I think, the least of worlds, but it could sit there for a long time with exponential time is the best you could do, who knows? So that's I like to see the world burn.
The most surprising things that I found about this claim is that it solved lattice problems within a polynomial approximation factor, a very small polynomial, and therefore it's not that big, and also for arbitrary lattices. And personally, if a quantum algorithm was going to come up, I would have expected it to be for perhaps a super polynomial, quasi-polynomial, say 2 to the polylog function, and for the type of algebraic lattices which are used for efficient lattice cryptography, where there is much more structure that perhaps would have been useful for quantum algorithms. And the fact that these results, this first quantum algorithm brought the problem in a way that we think of it as very strong is something that I found quite surprising.
This is fair, independently of whether it's right or not. It is a good motivation. Use of hybrid schemes.
Hybrid schemes, of course, one possible approach of NIST to the standardization process could have been, we collected these 80 or so submission, let's combine them into a single hybrid scheme such that if any of the submissions is secure, then the result is secure. So that would have been a very safe approach. And so considering hybrids is something that just between two things, and perhaps well tested what we are already using now and the post-quantum algorithm. This is something that I thought since the beginning would have been a good thing to do. At the same time, that's something that could be done separately, independently from standardizing post-quantum. So there could be a standardization process that could pick a post-quantum or a small set of post-quantum problems to focus on. Also to focus the cryptanalysis effort. So one of the advantages of having a small set of problems is that the few cryptanalysts that can work on breaking the systems, they can focus on those few things. And combining that to some kind of, it would be more like a mode of encryption where you use the system. Yeah, so I think that's something that would be highly advisable. And of course, when every single bit matters in terms of efficiency, then an hybrid solution can have a cost that is considered just too much. So of course, it doesn't come for free, but it's something that should be considered at least as mode of operation, a way to use the post-quantum cryptography.
2 seconds to push a record. Awesome. Thank you very much. That was a very high quality panel for such short notice. Thank you very much. Can we just have an extra round of applause for the people we put on the spot about something very hard? You almost know what.
We're going to have a 10-minute break, and at 2, we are all going to the zoo together and going to the ferry. Coming over to Toronto Zoo. Terminal, and we'll be back.
So 2 p.m. Where are we gathering exactly? I'm actually the pretty. Yeah.
Some of them. Organized, exactly. That's fantastic. Yeah, some of them. They have some person in action before. Yes. Yeah. Okay. Right. There are a lot of I think that okay, that's well, let's see my yeah, you don't know what's going on. That's it. Yeah, I think tomorrow is very good. Session. Yeah. What time? With you. Exactly. Still have some time. Yeah. Yeah, no, it's really exciting. It's cool. Oh, we should start. Oh, but your session's blue. You don't want to get this blue. Yeah. So, too. If we can. This one. Oh, so. So.